Today, continuing with exponentials and logs, we're going to graph exponential and logarithmic functions as well as use properties of logarithms to solve problems, evaluate, simplify, things of that nature. Okay? Make sure that you get done the goal. So that way you know what you begin with. Alright, so an exponential function is a function that's in the form of f of x equals a to the x. Okay? That's the form of an exponential function. A is a positive number, and a does not equal 1. Okay, this is your most basic exponential function. I guess you could always call it your parent function. There are two different types of exponential functions you have. You have exponential growth and exponential decay. And as you see up on the board, you have two different types. Okay? Your general forms, as well as their particular restrictions. Exponential decay functions, you'll know it's decaying, you know it should be decreasing if a is in between 0 and 1. And you'll know it's a growth function when a is greater than 1. The domain of your exponential functions is the set of all real numbers, okay? You probably could have told that based off the other graph. The range is a set of all positive numbers, okay? That's for either exponential growth or exponential decay. The curve does not intersect the x-axis, which means what's happening at the x-axis? There's an asymptote there.
Attention teachers, please.
So there's an asymptote there. Okay, is that y? It has a y-intercept of 0, 1. And there is a natural exponential function that has a base of e instead of a base of a number. Okay? Even though e does represent a specific type of number, it still has the same pattern, same style, same properties. So, alright, the same set of transformations that we had before with quadratics, with just any general functions, still apply here with exponential functions. Okay? So when you can see this now, again, if you know these transformations, you should have to write these down, right? It's more of a following along type thing, right? If you have plus k being added to your original parent function, remember our parent function here is f of x equals a to the x. So this plus k means it moves what? Up. This minus k means it moves down. When the plus k is inside of the exponent with the x, what's that mean? It means it moves to the left. And when it's a minus k, it means it moves how? To the right. To the right. Okay, the same types of transformations again that happened before. Remember with quadratics, the plus and the minus, if it was inside the parentheses, it meant it moved to the left and to the right. This one right here, when the x is negative, reflects where? Over the y. Okay? So it reflects the y-axis. And this one would mean what? And there's another number up there with the exponent. Say it was 2 to the 3x. That's what it would look like. What does that p mean? What does it do to the original parent function? This is the horizontal change of 1 over p. Remember, anything that's horizontal is the opposite. So that means the q would do what to the original parent function? Very good. It will stretch it vertically by a factor of q. And what I have over here, this is just an example, okay? So you have a function of 2 to the x, and then you have this g function here. That 3 means it should have been, what happened to the original function? Say it again. Vertically stretched by a factor of 3. It is a negative with the x, which means it got what? flipped over the y-axis, and as you see, the original parent function, which was the dotted, it got flipped, and so now, instead of being exponential growth, it's exponential decay. The -4 inside the exponent meant that it moved how?
Right.
Means it moved to the right by 4, and then the negative means it did what? It went down by 4, okay? And so if I take this point here, okay, remember every exponential function crosses the y-axis at 0, 1. Okay, so if I take 0, 1 and I stretch it vertically, well, it's going to stay, 0, 1. If it gets flipped off the y-axis, well, it's already on the y-axis, so it's going to stay there. But then it's going to move to the right 4 units, so 1, 2, 3, 4, and then it's going to move down 4 units, 1, 2, 3, 4. That ain't right. Did it move to the left? This is a minus. I believe it's a minus. Yeah, that's a minus. So if that move here.
They shut it off. They put it down to negative 4. So I think it
Yeah. So it changes to a 5. There we go. Yeah. Well, what happens when you pull from there to the next one? I'll tell you this wrong. Let's take this point. Okay, this point right here, 1, 2. If I vertically stretch it by a factor of 3, what does that point become? Think about it. If I vertically stretch, what's happening to that point? 1, 6. All my y's are going to get multiplied by 3, so I'm at 1, 6. Okay? And then that point gets flipped over the y-axis. So I'm here now. Then I move how? This is all types of wrong. Very much all types of wrong. So I move to the right, 4, and I should move down 5. So yeah, this is sorry, I guess I should check this. But do realize the same transformations still do apply. Okay? This is just a horribly drawn graph. But don't worry. We're going to do our own. We are going to do our own. And it's going to be correct. So here we go. We're going to graph 2 to the x, and we're going to graph 2 to the x minus 2 on the same axis, okay? So I'll give you guys about a 3-minute head start before I chime in. All right, so you have to graph the original parent, the original function of f of x, which is 2 to the x. And you can always, to graph any function, you can plug in points for x and get your corresponding y, okay? So if I were to do that for my f of x function, I can plug in -2, -1, 0, 1, 2, and see that when I do 2 to the -2, that's actually going to give me what? 1 over 4. If I plug in -1, that gives me 1/2. If I plug in 0, I get 1. And if you think about it, remember, every exponential function crosses the y-axis at 1. Plug in 1, I get 2. Plug in 2, I get 4. If I plugged in 3, I would get what number? 8. Okay? And when I draw my curve, I want to make sure that it is a smooth curve that should not, what? What do you think I want to say? Should not what? Should touch the x-axis, okay? So please make sure you draw a smooth curve that does not touch the x-axis. When you get close to it, it shouldn't touch. Okay? Because that's what they'll tell me on the mark scheme. They'll say award A1 for a smooth curve. You award A1 if it does not cross the asymptote, okay? So please make sure you do as such. So that -2 means what? So we're going to move to the right too. So that means that every point is going to move to the right too. So this point here is going to move here. This point here is going to move here. And just move everything over to units. And you basically draw these similar. Questions? Did everybody get that? Good stuff. You want a more challenging one? You should get another challenging one. We'll say that for later. Say that for later. Properties of logarithms. Switching over into logarithms. This is pretty much the most of the exponentials, okay? We already talked about solving exponentials, the laws of exponentials, and we just talked about the graphs of exponentials. So the main thing that you need to realize is that if you have an exponential function, b equals a to the x, then log base a of b equals x. So if b is a to the power of x, then x is the logarithm of b to base a. And this is definitely important to know. Okay? It's definitely important to know that. Okay, because it goes both ways. If they give you a log, or if they give you a problem in logarithmic form, you can convert to exponential by using that. And vice versa. You can go from exponential to log form using that. So that's very important. That is very important. No, I should say so probably. It's just the what you actually say to express it. Okay, and this is not in your reference booklet, okay? So you need to make sure that you know. Oh no, just kidding, it is in there. Topic 1. Okay, so it is in there. All right, so you definitely need to know, be able to use that. So if I wanted to evaluate log base 5 of 125, you can always write it in exponential form to figure that out. What's going to be my base in this problem? What's going to be my a for this problem? 5. And I'm going to raise it to x. Well, this would technically equal x, even though it doesn't have an equals x, you can put it there. So I'm going to have 5 to the x equals what? 125. And then knowing your powers of 5, you know that 5 to what power gives you 125? 3. So when you evaluate it, log base 5 of 125 is indeed 3.
You start out at the 5 and then you wrap around it, so it's 5 to the power of x and then equals 125.
For this one, I will set it up as my base, which is 64. I'm going to raise it to an x, and it's going to equal 4. How am I going to go from 64 to a particular power to give 4? Well, you know 4 cubed is 64.
4 to the power of.
Well, I don't know. I got the answer. X equals 2 over 5, right? No. Yeah.
Say it again. 1 over 3. If I'm going from a small number to a big number, like I was in this example here, then it's going to be a whole number. But if I'm going from a big number to a small number, then my x is going to have to end up being a fraction. Okay, so if you know that 4 to the third is 64, then 64 to the 1/3, or the cube root of 64, will give you 4. I know I'm trying to stick with your thinking. So if you say x to the 2/5, that would be the 5th root of 64, which would be decimal squared. So just be very careful. You can always check by plugging in and kind of doing it in your head. Okay, let's check this. 64 to the 1/3. Well, that's technically the cube root of 64, which is indeed 4. Whiteboards.
Hold on.
I want you to evaluate this expression on your whiteboard. You got 30 seconds. So write this in exponential form. That would be 3 to the x equals 1 over 81. Okay? Realize that 81, what's special about 81? It is a fraction. Well, 1 over 81. But 81, can it be rewritten to have a base of 3? Yes. How? 3 to the 4th. And if I want to not make it a fraction, what do I do to the exponent? How do I make something not a fraction? Or how do I make it to a whole number? Make it a negative. So x should have been a negative 4. Or you could have sit there and figure out, okay, well I know that 3 to the 4th is 81. I got to figure out how to make the fraction, so I just make it negative. That works too. But there's a little bit of work that goes along with it. Go ahead and clear your boards. Here's the next one. Rewrite this in exponential form. That's 5 to the x equals the square root of 5. You can also write square roots how? As a rational exponent. So since the bases are equal, x equals 1/2. So very good. Clear your boards. Write in exponential form, you have 5 to the x equals 125 to the 1/2. That 125 to the 1/2 was that b that's by itself on the other side of the equal sign, okay? Now, realize that 125 can be written to have a base of 5. What is 125 with a base of 5? And now that your bases are the same, you can set your exponents equal to each other. And what's 3 times 1/2? 3 halves. That should have been your answer there. Okay? Go ahead and clear your boards.
Hearts. Let's do a hard one.
I think I got a hard one. Here's the next one.
Right, right.
Yes. It was 100%. So yes. 9 to the x equals 1. There's only one thing that you can raise a number to get 1, and that is 0. So speaking of that, going back to your notes, that's the property of logarithms, okay? The log of any base raised to, the log of any base of 1 is always 0, okay? So just like you guys did on your whiteboards, you put in exponential form, there's only one possible number that you can be raised to get 1. Alright? I want you guys to do this next one, but you're going to do this one on your notes, okay? Do this one in your notes. You'll notice the change in size of the ones I want you guys to do on your whiteboards, okay? This is size 48 font, the other ones were like 100, okay? So this one in your notes. Okay, what you guys get? 1, very good. Write this in exponential form, and yes, x will equal 1. This is another property that I want you guys to get down in your notes, okay? So any log that has the same base of with the same number will equal 1, okay? So that's another property I want to make sure you guys add to your notes. Log base a of a is equal to 1, okay? Kind of like they cancel each other out. Now realize some log expressions are undefined, okay? For example, let's look at this one. It says log base 3 of negative 27. If I wanted to write this in exponential form, this would be 3 to the x equals negative 27. And just like that one problem that I think was on your homework, there's no possible number that you could raise 3 to get a negative 27. Okay? So do be aware. Now, if this was a negative 3, could you do it? Negative 3 to what power gives you negative 27? 3. Okay, so that's possible, but not this positive number. Okay? So this is not possible. So do be aware that with logs, you can't evaluate every log, okay? So that is another property that you need to make sure you get down. Log base a of b is undefined for any base a if b is negative, okay? And after you get done that property, I want you guys to do the next one. So what you guys get for an answer here? It is no solution. There's no number that you can plug in for x that will give you a 0, okay? So even log base a of 0 is undefined, okay? So that's another property there for your logarithms, okay? Now there's another property there for you. Okay, so a lot of properties for logarithms, okay? A lot of properties. Evaluate the next one. What did you guys get when you evaluated this? X equals 5. 2 to the x equals 2 to the 5th. So yes, since the bases are equal, you can set the exponents equal to each other. So that's another property. That's another property for logarithms. Now realize that all of these problems that I asked you to evaluate, you know, and they were associated with these properties. Okay, these properties are there to help you, to kind of save you some time. Don't get me wrong. I mean, if you forget what these properties are, you can always write them in the exponential form and figure it out, and then be like, oh wow, why did I even write 9 to the x equals 1 when I knew it should have been 0? I mean, yes, but you can always default to that, but it's going to save you some time because again, you are on a timed test. When you are in examples like this, find the value of x. If log base 2 of x equals 5, you can still write it in exponential form. How would this be written in exponential form? 2 to the 5th equals x. So it can be used to solve logarithmic equations. And what's x going to equal? 32. And there's your answer, okay? So you can use that particular feature from going to logarithmic form to exponential to solve logarithmic equations, okay? Whiteboards.
Also,
All right, here's the first one. Good job, raise your boards. Yes, 4 to the 3rd equals x, right, in exponential form. And you have 64 equals x. Here's the next one. So we write it in exponential form. You have x squared equals 64. When you solve for x, what do? Take the square root of 64. So you have x equals what? You sure? Yeah, and negative 8 times negative 8 is 64, isn't it? But okay? Actually, there's no but. It is plus or minus 8. Negative 8 and positive 8 would work. Okay? So yes, your bases can be negative. Okay? Yes?
so if that was like a 220 question, you just put A, B, or
It depends. Honestly, this probably could only be, it could be a 2-point, but you would have to have both to get both points. I have seen that. Here it is. I think there's one more. There we go. Right exponential. Why are you erasing? Did I say good job, 100%?
Oh, yeah. Come on, man.
2 to the negative 5 equals x. That negative, how do I turn into a positive? Make it into a fraction. And 2 to the 5th is what?
32.
So this is 1 over 32. And then C is 1 over 32 for everybody. Okay? Be careful. Here's the next, no, just kidding. Back to your notes. Dealing with logarithmic functions here. Okay? We're going to find the inverse of f, x, such that x. I'm sorry, 2 is to the x. Okay? Back to your notes. So what does that notation mean? F, colon, x, arrows. What's that? It just means f of x, okay? Do not forget about that. That notation just means f of x, okay? And you remember we actually found the inverse back in that very first unit dealing with functions. We did inverse work. What's the first step in finding the inverse of a function? You flip x and y. Well, do I have a y here? F of x. So I'm going to flip x and y. And now I'm going to solve for y. Okay, I got to get y out of that exponent. The only way to do that would be to what? Logs. How would I write this in logarithmic form?
You would have log x.
Like, is x my base or is x beside the log?
X would be your base.
Careful. 2 would be yours.
Okay, so you would have log.
And what will go beside right here?
Then you would have y. I was thinking of something different, the way we write it a different way.
But I want you guys to use that b equals a to the x, and then log. What was that? What was that thing that I boxed at the very beginning?
Log a b.
Okay. So whatever your exponent is what it will equal when you write it in exponential form. So log base 2 of x equals y. This will be your inverse. This will be your inverse for 2 to the x. So realize that exponential functions and logarithmic functions are inverses of each other. Okay? They are inverses of each other. So remember that inverse functions reflect over the line y equals x. Okay? Remember y equals x is a linear function with a slope of 1. Okay? So when you reflect, or when you have inverses, they reflect over that line y equals x. And this is just a diagram to show you just that, okay? Can I move forward? Okay? You want to add it in to get a quick sketch, okay? Now do realize that, think back to when we did inverses, okay? We flipped our x and our y. When you had a graph and inverse function back in unit 1, and I gave you a graph, what did you do to graph the inverse? If I gave you a graph, and I asked you to graph the inverse, what did you do to figure out the graph of the inverse? Flip what? You flip the x's and y's, you flip the points on the original, right? On an exponential function, we know for sure that one point is 0, 1, which is the y-intercept. So on the inverse, what would be a point on the inverse? 1, 0, which as you see here, that is indeed a point on your inverse. Okay? Look at y equals 2 to the x. There's another point, 1, 2. So on the inverse, it would be 2, 1, which you guys see right here, don't you? And it continues like that, so on and so forth. You have 3, 8, so you would have 8, 3, and you see that right here on this graph, okay? So same rules apply back in that first unit, okay? You just flip your x's and your y's, okay? What are some particular features for your logarithmic functions just looking at this example that I gave you? What's some other features? Yes? The asymptote this time is the y-axis instead of the x-axis like it was for the original exponential function. Okay, so everything flips. Everything flips, all the features. What was the domain of the original exponential function? What was the domain? All real numbers. So what does that mean for the inverse? All real numbers would be the domain?
Range.
It would be the range. So even that gets flipped. What's the range of your original exponential function?
0.
All positive numbers, 0 to infinity. Is 0 included? No, it's not. So then 0 to infinity would be the what for the inverse? The domain. And you see that right here. It looks like it's getting closer and closer to the y-axis, but never crossing or touching. Okay, so all of the features of the exponential function are flipped for your logarithmic function. And your transformations apply as well. Talk about all those features on the other slide. And then, of course, your transformations still apply as well, all right? If you're moving left and right, the number would be on the inside of the parentheses with the x. If you're moving up or down, you would have the log separate from the number. If the negative's on the inside, that means it got reflected over what? The y-axis, and then if it's on the outside, it got reflected over the x. So just be aware of that, and then, of course, your normal horizontal and vertical stretching and compressing. Okay, so do not forget about those. Just an example, okay? Just like the other one. All right, you have your asymptote of your y-axis, which is also x equals 0, okay? And it's increasing the the entire time, crossing the x-axis at 1, 0, so on and so forth. So let's graph this one without using a calculator, okay? Using those features there. So you have to graph the function -2 log x minus 1, okay? So what's happening to our original function here? Our original log function, what's happening? It's going to the right one. It's being flipped over the x-axis, and then it's being vertically stretched by a factor of 2, yes? Okay, now one thing that's a little bit different from the other ones is what's your base? It's 10, okay? Your base is 10. Whenever there's not a number right here, and there's always a 10 there, okay? So 10 is your base, so if you wanted to do an exponential function here, it would be 10 as that base, okay? So, to graph this, how would I graph this? How would I graph this? I'll be quiet now. I saw some of y'all not taking notes like you knew this already. So how would I graph this? Let's go. Be quiet now. Yeah, I think that would be a good way to start. Make a table, get some points. At least of the original graph of log base 10 of x, because then once you know that, then you can move it left and then vertically and flip it and everything that you gotta do, okay? So let's make a table here. Which value should I use? Think about it. Can I say the log of the negative number? So I might want to stray away from my negatives. I shouldn't use 0 because there's a what? There's an asymptote in 0. Well, I think what Tommy was getting is by making a table, we can find our original function and then move that one. See what I mean? So, I mean, we could use 1.
Wouldn't the original function be always what we had at the beginning where it's 1, 0, or sorry, 0, 1,
No, you meant 1, 0. It always crosses the x-axis at 1, 0. It's log, not exponential, it's log. It always crosses the x-axis at 1, 0. But I probably want another point to kind of help me out here. What's another point on the original log base 10 of x function? What's another point? What's another point I could have to give me a really good set? Other way around. 10, 1. 10, 1. Think about it, okay? If you had this, right? 10 to the 0 equals what? It will equal 1. So x will be 1 when y is 0. Log base 10 of x equals 1. 10 to the first would equal x. So x would be what? 10. So 10, 1 is another point I could graph as well on my original parent function of log base 10 of x. Those are the points that you should move and alter to graph this function. Okay? So, because it doesn't shoot up and off very thin. So let's take our points. 1, 0. What needs to happen to it? Stretched by 2. So 1, 0 would turn into, stay the same thing, 1, 0. And then the negative would do what? The negative 1 will move over to the right. What about that negative on the outside of 2? Move it over the x-axis, so would it change? No, so this is now here. And also if I move it over to the right, my asymptote is also moved as well. What about this point of 10, 1? Vertically stretch it by 2 would turn into what? 10, 2. Flipping it over the x-axis, 10, negative 2, and then moving it over to the right one, we'll put it
11.
Now I have a question. What's it gonna look like? Like, help me out here. I thought I was gonna be doing this number here. Why am I not gonna do that? It's flipped, so it's gonna go down. It's gonna decrease. So there it is. If you can figure out what your parent function is, that will probably be your best bet. If you're sitting there trying to plug in points, especially without a calculator, you're trying to figure out, okay, well, 10 to what power is going to give me 3 because I plugged in 2 for x. See what I mean? So just keep that in mind. Questions? So yes, the log on your calculator is the base of 10. Hopefully you haven't forgotten that. And then do realize that if there isn't a log ready, it's to a base of 10. So that's log base 10 of x. Your inverse, your respective inverse. Log base 2, very simple enough. You pull out your calculator, you type it in. Those are the only constants you can't do in your calculator. You can't do log base 3 of 2. You can't do that there. Well, not by just pressing log and then you have one of the newer ones?
Yeah, not using that, something.
You can change it.
Okay. On your exam, you're going to have these, and that's not the third version. So, you're going to need to know another formula to be able to do that. Also, natural logs are logs that are written with the base of e. Okay? Don't forget about those. It's the same. That's the ln of x. Lastly, ln of x is the inverse of the exponential function e to the x. Just like with logs, they're a reflection over the line y equals x, as you can see in this picture here. And then here are a few more properties that I would suggest that you guys would write down that involve your logs, your natural logs, and that natural exponential function.